So Professor Naren is our esteemed faculty partner of OpenFOAM team FOSSEE, and he has guided several students for the internship and fellowship of OpenFOAM team FOSSEE. He's a very well-known teacher and researcher, and we are really fortunate to have him in our team.
So I'm very happy to be as part of this program. In this talk for the next 30 minutes, I'm just going to introduce the snapshots of what is multiphase flow and what are the broad modeling methodologies for the multiphase flows, and then leave the session and to be continued by, and then from FOSSEE, they'll take it on two sample cases. One is, I think, a droplet dynamics, and another is on the bubble column. So that's I think the plan for this session. Now, before that, this is something an interesting website which I want all of you to look into it if you are a fluid mechanics enthusiast. This is called Gallery of Fluid Motion. If you just go to Google and then put Gallery of Fluid Motion, this is one of the first link. You will also have a YouTube of American Physical Society which hosts this, but you will get to this website. And if you click here, previous galleries, right, you can go into any of these, and you will be able to see fascinating videos of how different fluid contacting patterns are there, right? Some of these are available in YouTube, some of these are only available in this website, but this is something, a source of an enthusiast if you are a fluid mechanics. This has lot of different types of fluid flow motion in terms of liquid, gas, liquid, solid, and so forth. But just have a look into it. So this is what first I just want, before even I start the presentation, I just want that please look into this gallery of fluid mechanics. So if you just go to Google, put Gallery of Fluid Motions, you will get into this. And this is from the American Physical Society. Now, with this as a starting trigger, we will focus now on what is multiphase flows. Before I go into the technical part, I wish to first convey my gratitude to Professor Kannan Morgalia, Professor Janani, I think, who is supposed to is conducting these OpenFOAM sessions, and I think he is also going to conduct a follow-up session. And of course, the whole part of the FOSSEE team, Payal Madam, and the audience. I have kept the presentation very simple so that the idea is not to make everybody an expert in just 20 minutes or 30 minutes, but to introduce to them what are the salient features of multiphase flow. These are some of the references. You can go back and read them, and that will help you to learn a little more better on CFD and multiphase flows. Especially if you wish to do something in terms of chemical reaction modeling or involving reaction, I would prefer you to, I would help you to read this Jacobson book. This Kroll's book is like a kind of standard multiphase handbook, which will help you know about the different technicalities with respect to the multiphase flows. So by now, I think you are very clear that what you are doing in fluid mechanics or in CFD, we are trying to simulate the fluid flow within the concept of something which is, we call it as continuum. What do you mean by continuum? In a sense, we don't see the molecular phases. If you see here on the left, what you see here is actually a water molecule, but this is a molecular view, and you will see a lot of empty spaces. This is not something that we are seeing in fluid mechanics. What we see in CFD is something like this. We see as though the space is continuously filled with the fluid. This concept of continuum is based on something, a dimensionless number, which we call as Knudsen number. So that means it is either lambda by L or L by lambda. Lambda actually tells the mean free path of the molecule. So that means between two collisions, how much distance the molecule travels. L is a characteristic dimension of the system. Right? And I'm sure that all participants would have gone, have at least a fair idea of what are the governing equations that we solve in CFD. We solve primarily the continuity equation, which is actually the equation of mass. we solve the Navier-Stokes equation, which is the momentum balance equation. Obviously, when you have energy, if at all, if there is a thermal difference or there is a temperature distribution, we solve the conservation of energy. And if there are reactions, we solve something called species transport, which I have not written here. All these are called the transport equation. Now, all these are again tied to something which is called control volume. We are taking a volume which is so small, yet we will not see any discontinuities. We will still see matter to be continuous within that small, it is infinitesimally small or a fictitious volume. So that's the concept of control volume. Now, with this, we can represent all the equations that we use. I mean, the mathematical model based on which CFD, we are predicting the fluid flow as one equation which is represented here. In this, if you change this phi to any of these, you will get the respective equation. So that means if you make this phi as 1, you will get it something called continuity equation. Instead of this phi, if you make it as velocity, which can be u, v, or w in terms of the respective direction, then you will get actually the momentum balance. And obviously, similarly for energy balance and the species balance. These are nothing but the flux terms. These are nothing but the molecular diffusion terms. These are the source terms of the sink term. For example, for the Navier-Stokes equation, the source is typically the pressure drop gradient. So that means the pressure difference across 2 points acts as source. And similarly, the gravity term acts as a source because that causes the fluid motion, so it is actually the source. Now, what is this diffusion term in terms of Navier-Stokes? This is basically given by the Newton's law of viscosity. If it is going to be a laminar flow, we will just incorporate Newton's law of viscosity. Otherwise, if it is a turbulent flow, then we need to add the turbulent contribution to the shear stress distribution also. So we can represent this as one equation wherein by changing this terms of phi, you can get the respective transport equation. All these transport equation will follow this general principle wherein accumulation plus net outflow is equal to net diffusion plus net source flow. Now I have given here as net, the word net. The word net denotes here, it is like output minus input. So when I say net outflow, it is outflow minus inflow. Why I'm saying is net diffusion, because diffusion can occur both at the inlet and the outlet. So this is net diffusion. This is like out minus in. Similarly for the source term, right? And all these terms are usually per unit volume per unit time, right? Somebody has said the negative pressure gradient is missing. Yeah, here I have not incorporated the sign actually. I have just told what are these terms. In fact, for the gravity also, depending on what direction the flow is there, this will actually have plus or minus. So that's perfect. Somebody is very sharp. So here I have not told the signs. I have only told the broad nature of the term. Depending on the flow direction, depending on how the flow is orientation, you will actually have the sign convention also being added into it. That's why all these things are in return generally as net. Now let's go into the multiphase flows. I'm just going to very quickly move through different types of contacting patterns that you observe. Now the difference between this is for a single phase flow. What you see in slide 8, this transport equation, this is actually for a phase. This is not for multi-phase. This is so long what you have been doing is for a single phase flows. If you have a liquid flowing through a pipe, if you have a water flowing through a pipe, or if it is a stir tank, we are only focused on one particular fluid flow. But what happens in multi-phase flow is more than one phase flows. So that means you will have either a gas liquid, you can have a liquid, you can have a liquid solid, or you can have a gas liquid solid. So more than one phase, more than one thermodynamic phase coexist in the system. This is what, before the start of the presentation, I asked you to even check into the gallery of fluid motion where you can see different type of contacting patterns. Now, based on whether they are horizontal flows, vertical flows, whether they are gas liquid systems or a liquid liquid systems, we can have different types of these contacting patterns. So for example, this is called dispersed phase flow. Why it's called dispersed phase flow? Because you have one phase which is almost continuous, which you see in light blue color. And you have another phase which is like here droplets seen all over the system. So this is something called dispersed. Whereas if you see in the bottom, these are called stratified flows. Why they are stratified flows? This is primarily one fluid phase, and this is another fluid phase. So you primarily have two fluid phases. They are still co-flowing, but they are only in contact through this surface which separates them. So that is why this is stratified flow. This is in terms of horizontal gas liquid flows. You also have this in vertical flows. So this is a picture for a vertical flow where again you will have something like a dispersed phase flows to something like a stratified or annular flow in this case. These flow regions and how they occur and what condition or what will occur, it all depends on the hydrodynamic parameters on the operating condition. So different people have given something called flow regime map. Now this flow regime map helps us to understand at a given condition which of these contacting patterns happens. And now, like for example, what you see here is a contacting regime map for gas liquid system, but now it is written in terms of flux. Now you can again have this is for horizontal flow, this is for a vertical flow, again in a different velocity as the abscissa and in the ordinate. This is actually for a three-phase flow, so where you actually have a aqueous, you have an oil phase or a organic phase, and then how it gets dispersed. Right? Now this is for a gas solid system again, now where again you can have multiple patterns. Now, the idea is something like this. So, what we know as of now is if there are more than one phases coexisting, then there can be different flow patterns, and these different flow patterns affect the performance of that particular equipment. Now, that equipment can be a two-phase flow heat exchanger. That equipment can be a reactor in a sense. If you think of a petrochemical complex, if you think of refining systems, all these are primarily a gas liquid systems, right? Or gas liquid solid catalytic system. Their performance in terms of their reaction or how much heat can be recovered or how much a particular process can occur depends on how these phases get distributed. This distribution of phases affects the contacting area, and this contacting area eventually affects what is the performance in the system. So that means we need to predict these performance based on these hydrodynamic features. Now, one thing which I'm shown here is from one of my colleagues along during my PhD times from NCL. What they have done is taken a boiler, right, and then they have tried to predict what happens in a boiler as the heat is being conveyed and it goes to the different primary and the secondary heat exchangers. What you see here is how is a flame zone, and this is how the temperature distribution happens, and eventually how the heat is being convected. Now, if we want to model completely this, then that means we need to model this contacting pattern. We need to model how these two phases coexist. Now, that means we need to predict now how a dispersed phase and a continuous phase, a primary phase and a secondary phase flows together. What happens, how they get distributed, what would be their phase holdup. What do you mean by phase holdup is on a per unit volume, how much of one phase will be distributed in another phase. And whether both of them are going to affect one another, or it is only one way it is going to affect, or it is the turbulence of also both the phases are going to coexist. All this will determine how this multi-phase flow pattern exists. Now, with this, something what we broadly have in the modeling of multi-phase flow is something called volume of fluid, Eulerian-Lagrangian, and Eulerian system. Right? So that means we broadly have three types of modeling patterns. So one is the Eulerian, which is also called the two-fluid model. We have something called Eulerian-Lagrangian, which is the dispersed phase model. This is called dispersed phase model. And we something have volume of fluid. All this depends on what are we interested to see, or that means to simulate. If we are interested to see the surface or shape or how the interface between two phases exist. So that means if you have a chamber or if you have a system, let's say this is filled with gas, and if you put a droplet, if you put a liquid droplet, you know that as the liquid droplet falls, it may change different shape. If you are interested in capturing this surface, if you are interested in capturing this surface, then this we do by something called volume of fluid approach. So in volume of fluid approach, we track the interface. We track the interface of each of the dispersed phase. So that means if there are 10 bubbles, we will capture the interface of all the 10 bubbles have to be tracked. It's not just one. Suppose if I put multiple droplets here, so that means each of these droplets, for each of these, we need an equation. So that means if there are n droplets, we will have n equation to track n surfaces. Now, in some situation, this is what is the objective. The objective is to track the shape. The objective is to track the surface. Like for example, where this could be important. Suppose let us think of a spray where you are spraying a fuel. It can be a fuel injection system, so as part of automobile, or it can be as a part of a burner. Now, if you spray a fuel, the injection characteristics, will affect the size of the droplet or the bubble, right? Eventually, the liquid droplet, the fuel droplet has to vaporize, and that vaporization will affect the combustion dynamics. Now, this not be just in the fuel system, you can even think in terms of a deodorant. So if you have a deodorant spray, now we use a lot of liquid deodorants. When we spray the deodorant scent vaporizer, we get it as a liquid droplets, and the size of the droplet and the shape of the droplet will eventually govern how far is that deodorant is effective. In a sense, how far we see that particular vaporizer, we see that particular scent or deodorant as effective. If these are something that we are going to model, then that means we actually need to do the WAF. So in WAF, what is the primary equation? You actually have one transport equation for the primary phase and one each for each of the secondary phase. So this is essentially the same equation that you have seen as Navier Stokes, but only thing the number of equations are more, and how they are coupled, their interface is coupled by the surface tension force, because it is essentially the surface tension that helps you to track the interface. So the two phases are getting coupled through the interface momentum transfer. So in that interface momentum transfer, one of the key part is actually the surface tension of one phase in another. Now, in some cases, we are not interested in shape. We are interested in how much of dispersed phase is present. So when I say how much, it is volume of dispersed phase to the total volume. We are interested in this fraction. This fraction is called phase holder, usually given a symbol epsilon. So epsilon of I means volume of the dispersed phase I with respect to the total volume, right? Suppose if you have a system here, which is actually having a primary phase, and suppose if there are now secondary phase, whatever I am showing in blue color is actually the secondary phase. Now, what I'm drawing is not the actual shape. We are not worried of actual shape or size, because you cannot see the shape or size in terms of the EE model. But what we wanted to know is what is the volume of this whatever I have represented as a blue phase divided by the total volume. So that means is it 10% of this space is occupied by the dispersed space, 1%. This is what is something of interest. So now the objective is not the shape, not the size. We are not worried about the shape or size. We are worried about where is the liquid or where is the dispersed phase or where is the gas, which is the dispersed phase. It's present in the primary phase. So in the matrix of primary phase, where are the dispersed phase located? So we wanted to know what is the dispersed phase holdup and its distribution. Now, when I say distribution, I am not talking about size distribution. I am talking about how epsilon varies with respect to XYZ, right? With respect to position, how it varies. Suppose if you have a column, say let's say a bubble column, which is let's say filled with liquid, and in that, suppose if you spark gas, so if you spark from gas, it may form bubble. Remember, what I'm drawing now in blue is not the actual shape. I'm just figuratively representing as though there are like a gas phase. Now, gas phase, this could be like this. Now, if you clearly look into this cross section, it is not everywhere that the gas is there. Gas is there in this region more, whereas it is very less in the other region, right? So this is what is called the distribution of the holdup in a particular column or in a particular reactor. We are interested to predict this. Why we are interested to predict this? Because this holdup again tells how much phase is there. This how much phase will tell whether reaction will happen or heat transfer will happen or mass transfer, phase transfer will happen. And this will eventually govern what will be the output. What will be the output from that particular column or that particular equipment. So we are interested in this phase holdup. This is what is your interest. Then we do something called TFF, which is also called EE or Eulerian or two fluid model. In the two fluid model, you have one equation for the primary phase and one equation for the dispersed phase. In contrast, if you see the volume of fluid, if there are 10 bubbles, there are 10 equations for each of the bubble. Here you don't have 10 equations, you have only one equation for the primary phase and one equation for the dispersed phase. And these are coupled. How are these two equations connected? Because if you don't connect these equations, then it's like they don't talk to one another and then you cannot solve them and get it. So they are connected by something which is called momentum exchange factors. Now, we know this factor for a long time, but not in this word. Like, for example, drag force. Drag force is one type of momentum exchange factor. There are other such forces also, something called lift force. You have called Bassett history force, and so on and so forth. So that means these are nothing but interaction terms. They are primarily force terms. They depend on how far is the velocity difference is there between the two phases. So what I write here as del U is nothing but velocity of the primary phase minus velocity of the dispersed phase. It can be written as either way also. So this force is proportional to the difference in velocity between the primary phase and the secondary phase. It is proportional to the what is the area of the dispersed phase. Obviously, it is proportional to the density difference between the continuous phase and the dispersed phase, or the primary phase and the dispersed phase. And there's obviously a proportionality constant, and the proportionality constant is nothing but the coefficient of that force. So if it is a drag force, it is called the drag coefficient, or if it is a lift force, it's called lift coefficient, and so on and so forth. Now, this momentum exchange factor is what needs to be introduced in the model. So when we simulate a model, you will show in the next session that we will specify these forces. Predominantly, this drag force is what is specified, and there are different correlations available for this drag coefficient. So when we specify this drag coefficient, we will end up simulating the two fluid model or the oily-rain model, wherein the objective is to get the hold-up distribution. I'm not going in detail about Eulerian-Lagrangian model, but I'll just tell you what is the objective behind Eulerian-Lagrangian model. In the Eulerian-Lagrangian model, the focus is to track the motion, of the dispersed phase. So if you are interested in shape and size, we do WAF. If you are interested in the phase hold-up distribution, what is their volume percentage, how are they present, then we do the two fluid model. The Eulerian-Lagrangian model, here we track the motion. We are interested in the path that is traveled by the dispersed phase. So based on what is expected objective in a multiphase flow, three different modeling approaches are being used. I think in the practical session, you are going to take a single droplet and do it. So you are going to do a droplet. So that means where you will take a single bubble. You can also take a single liquid droplet or a bubble, and then see how the shape changes. That you do about WAF. And I think then you are going to see something in a bubble column. So in a bubble column simulation, you will take primarily a column, fill it with liquid, and then you will sparge it with a gas and then see how the gas distribution occurs. So this is primarily the hold-up distribution, right? That is what you are going to see in the practical session. So I think this is enough for a very, very brief introduction. For detecting cavitation, what is recommended usually is to, okay. So if you want to detect cavitation, right, from your question, your idea is you want to have cavitation to be seen. So that means you want to simulate this. Now that means you don't want to see the bubble size or shape. You are primarily interested to see how much volume of a given space is being occupied by the cavitating bubbles. If this is the case, we can do by two fluid model, but only thing we need to add something called the source term. Now, why we need to add a source term? CFD by itself does not know that it has to change a liquid to a vapor state. Because usually when cavitation happens, the pressure in a particular point goes below the saturated vapor pressure. So if the pressure in a liquid goes below the saturated vapor pressure, you will have a liquid to vapor transition. This liquid to vapor transition is the result for generating that vapor. This CFD will simulate. Okay, it will simulate and it will show you that at a particular point, the pressure is less than the saturated vapor pressure. But this CFD will not have implicitly. We need to write this as a subroutine, or you need to give it as an external code, right? So what I mean by this is you need to tell how much vapor needs to be generated. So in a sense, the rate of generation of vapor. This rate of generation of vapor anyhow is proportional to this pressure drop. What I call this as pressure drop is not the actual pressure drop in the fluid phase. It is the pressure drop in the fluid minus the saturated vapor pressure. Only if this term is positive, this source term will get activated. Only if it is becoming negative, if it is becoming less than that, it will get activated. Otherwise, if the pressure is greater than the saturated vapor pressure, this source term will be off. So that means you will not see a vapor. So I think that's on the cavitation question. Any other method possible to detect cavitation? I think if you're asking in terms of experiments, how to detect, one way to detect is to have an ultrasonic horn. If you see papers on cavitation, they would usually have an ultrasonic horn. So there's something like how we have a medical stethoscope, right? So we can have that stethoscope attached to the outer part of a system. It could be a pipe or it could be a reactor where you are expecting a cavitation. And because when these cavities burst, they release sound waves, and these sharp sound waves can be detected by these stethoscopes, and that will act as a detection of the presence of this cavitation. Now, we can't use X-ray because, in a sense, it's not going to be a very permanent when the cavitation happens, the bubbles are generated for a microsecond, right? And that may not be detected by an X-ray. So to detect an X-ray, you need some kind of interference with that X-rays, right? So that means you may give an X-ray, or let's say it could be a gamma ray tomography or whatever it is, and obviously you will not be able to focus this on a very large part. The best, easier way is to use the sound waves itself, because at least it is non-harming. Because having an X-ray for a very large part, I don't think it is viable, because these are ionic radiations. So it is better to use sound waves to detect, sound horns, or what you call as stethoscopes, to detect. Okay, so I think that's all I have for the day, and I wish all the participants to have a very good practical session with John. John, you can carry on.
Yes,
Thank you.
sir. Thank you so much, sir.
Thank you so much.
Okay, thank you.